All right, next up, this corresponds to problem 24. We're just going to be talking about gravitation and also centripetal force, which is distantly related, but it's important because they both come together in these problems. So to start off with gravitation, we most commonly know like gravity is just to be an acceleration that pulls things down at 9.81 meters per second. But if we look at the macro scale between planets and stuff like that, it becomes a lot more complicated. Newton made the equation force due to gravity between one planet to another equals g, which is a constant, gravitational constant. It's a very, very small number, times m, I guess you can call 1 m2 over r squared. And this is where we have m1 and again, Newton's third law, they each exert forces on each other. So even though m2 might be a lot smaller, it's still exerting a force on m1, and since m1 is more mass, you just don't notice it accelerate that much. And so this is the famous equation for gravity, and most of the time when we look at things in orbit, it's not accelerating towards the other object. There's a force that's keeping it, not keeping it in place, keeping it orbiting. It's a bad drawing, but keeping it orbiting the planet, not accelerating straight towards the planet. And that force is centripetal force. Now, when we spin things like around and around and around, there's a tendency and a force that pushes the things towards the very edge. It pushes them away from the object that it's spinning around. It pushes them out. Like, it's a force that can come in from many different ways. It can come from like tension, it can come from gravity, it can come from like normal force, it can come from friction. But it's a force that basically keeps it in place. And the way we calculate the force is mass times acceleration, and centripetal acceleration is defined as v squared over r. So therefore, centripetal force is the mv squared over r. And we never call it centripetal force because it's not inherently a force in itself, but it's a force that can take the form of many other forces, like it could be gravity, it could be tension, but this is the force that's keeping it out, it's pushing it out. It always pushes away from the center of rotation. So when we have these two different formulas for the force of gravity, then we can find out a lot of other things, and we can set up equations to solve for other variables that we won't have, which is what we will do in problem 24. All right, problem 24, we have a sun and two satellites. One's an inner orbit of radius r1, and it's moving around, it has mass 1, and it has velocity v1. And the other satellite is an outer orbit, radius 2, mass 2, and velocity 2. And 24 asks what the ratio of the different velocities of these two objects, v1 to v2, is. And so the way we start this out is by taking, start with mass 1, or satellite 1. We know that the gravitational force between the satellite and the sun is gm1m sun gmm over r, and over r squared. And that's basically the force that's keeping m1 in orbit, satellite 1 in orbit. And we know, because it's in uniform circular motion, that that force is also equal to mass times acceleration, which is, the acceleration is v1 squared over r1. This is r1, by the way. So with this relationship, we can see that dividing by m on either side cancels out. We can see that there's an r1 in the denominator that can cancel out. And we are left with v1 squared equals g, the gravitational constant, times the mass of the sun over r1. And now, if we repeat the same exact process with satellite 2, we have gm2 m sun over r2 squared. It's the same process. dot, 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 and we end up with velocity 2 squared equals constant GMS over R2. And now the question asks us for the ratio of the speeds, V1 to V2. So if we take this equation and we divide it by that equation, up here we get V1 over V2 all squared equals this divided by that, and we can see that this is a constant and this is also a constant. So that will cancel out, and we end up with 1 over R1 over 1 over R2. And rearranging this, we get equals to R2 over R1. And we take the square root of that side, we end up with V1 over V2, the ratio of their speeds, is equal to the square root of the opposite ratio of their radii, which becomes answer choice A.